we're going to learn all about the scientific method, okay? But before we begin and before we get into any steps, we're going to do a little exercise. So what I'm going to do is I have this candle up here, okay? I'm going to put it up here. I'm going to set a timer for about 2 minutes, and at roughly 1 minute, I'll light it for you. What I want you to do during this time is I want you to make observations about it. Thinking about if you had to describe this candle to someone who was not in this room with us so that they could replicate this candle, what information would they need? Okay? Thinking about that. So what type of information did we gather about it?
Cylinder, white, rubber-like appearance, made of wax, about hand length, so 5 3/4 inch by 2 3/4 inch circumference, and weighs about 460 grams. Brooks was originally white, but burns.
Wow, lots of info. So I heard cylinder and white. I heard 450-ish grams. How tall did you say?
5 3/4 inch.
5 3/4 inches.
2 3/4
2
circumference.
3/4 circumference. Okay, so lots of info about it. Okay, what you just did, and you don't feel like you need to have to write down all of the measurements that I just put on the board, okay? Because what you just did was the very first step of the scientific method, okay? And that is to make some observations. Now you're going to notice we talked in our bell ringer about the scientific method, and you all had different steps, and these steps that I'm listing out for you, air quotes around steps, are going to probably be different than ones you've heard in the past in other courses, different than the ones you remember, okay? And that's because the scientific method isn't just a list of steps of check boxes that you have to check every time you do science. It's a process. So in general, this is what the process looks like, okay? Observing, we start by making measurements and collecting data. That data can come in 2 different types. It can come as qualitative, which we would say is descriptive. So that would be when you were saying color or how it felt in your hand. It was waxy, you said, okay? And then data can also be quantitative, okay? So quantitative data is hard numbers, numerical values. So when you gathered the mass or the height or the circumference of this candle, you were getting quantitative data. Okay. Once you have your data, you can start to define your system. Your system is the specific region, area, location, objects that you are going to use when you are running your tests. The best way I can help you understand this is by giving you an example. So for example, if you were going to run an experiment in which you were testing boiling water, the beaker and the hot plate and the water that you were using would be your system. Okay, so your system is the small area within which you are taking measurements. If you were trying to gather data about, number of pigs in the state of Nebraska, your system would be the state of Nebraska. So it depends on what your experiment is, how big your system that you are measuring is. The next step is, as you guys correctly identified during the bell ringer, formulating a hypothesis. So hypotheses are generalizations. So as you're gathering data, you're going to look at this data and you're going to start making these generalizations about the data. Okay? They need to be testable, and they should be specific and supported by data, because the purpose of making this is to make predictions about the future. So they need to be specific, need to be supported by data, and they need to be testable. Okay? So, for example, let's say I gathered data about the number of sick hogs in the state of Nebraska. Okay? If I was going to make a hypothesis about it, It wouldn't be okay to just say there are more sick sows than there are sick boars, right? It needs to be very specific, and it needs to be supported by data. So if I'm making a generalization, I could say there are more sick sows because the process of breeding puts more stress on them than on boars. Notice how that's supported by data. There's a piece of data in there that I'm saying supports my hypothesis. Okay, so I've got this generalization that I've gathered from the data. There's this idea sometimes, and I think it's perpetuated by science classrooms, that your hypothesis should be this brand new answer to a question. And so sometimes we make these hypotheses that don't have any backing data to support them. Your hypothesis should naturally come from the data that you have observed. Okay, so if you're observing students in a school and trying to figure out how what causes them to be late to class, then your hypothesis should be based on what you observed. You shouldn't observe students running late to class for appointments and sports activities and, playing and chatting in the hallway with their friends, and then say, I think students are late to class because the bells aren't loud enough, right? That's not supported by the data that you saw. Your hypothesis needs to come back to your data in order for anybody to take it seriously. No one's going to spend money funding research to test a hypothesis that doesn't have any background support, that doesn't seem like it could possibly be the reason for this thing happening. Okay? Now comes the fun part. Make the cookies. Mrs. Von Laub will give you ingredients. You will make the cookies. Okay. I won't leave you in suspense for too long. What else do you need from me in order to successfully make your cookies?
We need heat. We have a microwave.
I don't know. That we could conform.
Michaela asks for it.
Eggs.
No, at the very beginning. What did you say?
Did I say?
Is there a recipe? She said.
At the back of the.
This would be an awful lot easier if I gave you instructions, right? So here are some instructions for 3-ingredient no-bake cookies.
Yummy.
All right, so go ahead now and follow the instructions to make them. So you needed instructions from me. This whole demonstration has a purpose, and we'll get to that. We're gonna hop back on over to the notes. I promise it will make sense in a minute. Okay?
I was all about making our own.
All about making the own cookies, okay? So the next step is testing, okay? Once you have your predictions, you have your generalization hypothesis, and you have your prediction about what you think you're going to find, then you can start testing. The first thing you have to do is identify variables, what things you can control and what things you're going to change, okay? So when you made the cookies, what were the variables? Ingredients, also how you combine the ingredients and what you did with them when you were done. Anything that would affect the outcome of the cookie is a variable, right? So how long you leave it in the fridge, how much of each ingredient you put in, what brand of ingredient you use could even affect the outcome. It could affect your final cookie experience, okay? So when we're doing science, we have to identify as many variables as we can, and it's our job to try and control as many variables as we can, because if I made these cookies, but I added more honey and more oats and more peanut butter than they said, and I didn't like my cookie experience at the end of it, could I point back to any one thing that caused that? No, because I changed too many things. So in science, we change only one variable. If possible, we control everything else so that when we get to the outcome, we know that the cause of that outcome is the variable that we changed, because otherwise there's no way to tell. So we want to control as much as possible. It's not always possible to control everything, but we try to control as much as we can, okay? if our testing then doesn't support our hypothesis, we have to discard our hypothesis and or modify it. So if we go back to my example with the hog survey, right? If we do a survey of like the conditions that the hogs are living in and everything, and we discover that the conditions, the process of birthing is not more stressful on the hogs than not, we would have to discard our hypothesis about why that there are more sick female hogs, right? We'd have to discard that. But if it was supported by that data, then we would move on from there. But if it's not supported, you have to either throw out the hypothesis and start fresh, or you have to modify your hypothesis and try again. Your data needs to be recorded in a way that allows for replication and repetition of your experiment. Okay? So that's the whole point of a recipe, right? When I asked you to make the cookie, you kind of looked at me and one of you was like, well, could we get a recipe, please? Because you know that in my brain, I have a cookie experience that I'm expecting. But without instructions, you don't know how to get to that cookie experience at the end. So you need those instructions to detail to you how to get to that. The same is true for science. If somebody else wants to do your experiment and they want to do it the same way you did to see if your results were accurate, they need to be able to follow your process exactly. So in science, we get even more specific than a cookie recipe, because a cookie recipe will tell you how much of each ingredient to add, and it will tell you what temperature to cook it at, and that's usually what you get. They might tell you a little bit about what things to combine first, right? If you're getting into a really pretentious cookie recipe, they might even tell you you need this specific brand of sea salt or the cookie is ruined, you know? So they're not super detailed, but they're detailed enough to get you roughly the cookie experience that you want. But in science, we have to be more detailed than that. If the cookies were a scientific experiment, you would have brand names, detailed weight amounts of every ingredient, step-by-step instructions about what temperatures and conditions were like in the labs when you combined those ingredients, how long you stirred them for, what size of ball you shaped them into, what methods you used to shape them, how long you put them in the oven, what brand of oven, what specific temperature was the oven at. There would be so many more details, because the goal is that someone else be able to step in and replicate your experiment exactly. Okay? The end point of this is exact replication for the purpose of double checking. Okay? Because if your hypothesis is supported repeatedly, it starts to form the basis for a theory. So if we do experiment after experiment after experiment, and the data continues to support your hypothesis, we start to shape that into a theory. A theory may be a more generalized explanation for something. Okay? It's going to be bigger and broader. Okay? So somebody who was studying temperatures in the mantle of the earth, then their overall general theory that they come up with might have more to do with how the plates on the surface of the earth move due to that heating, and then we get this general picture, this theory of how some phenomenon works. Theories often inspire a model. Now, oftentimes in science, we think of a model as just a representation of an object, right? Something that's too big or too small to see. But a model can also be an explanation, a thing that describes how a process occurs. And that's the kind of theories and models that we're talking about here. They're going to give you a model. So I come back to the idea of the theory of plate tectonics, because in my educational career so far, the theory of how those plates move around has changed several times as we gathered more evidence and revised our hypothesis and came up with new theories. So this process is continuously going, because in science, we can never prove, we can only disprove. Okay, science doesn't allow us to prove something correct because with science we have to assume that technology is always getting better. More data is always being gained, and we may come across something down the line that disproves what we thought for sure was true. So we always say this is our most current, best theory of how this works, but should new data arise, we would revise this. We're saying this is our best explanation right now. We're not saying that it's true, but we're saying that all of these things that we've tested and proven incorrect are not the way it works. This is our best guess right now. Okay? And then the last step is to publish your results. This goes back to, the reason for publishing your results goes back to that testing phase, because we want other people to be able to read about our experiment, gain that information, and then duplicate it and check us. Science relies heavily on peer review, so we want other people to come to the same conclusions, because you never know what happened in your experiment that went wrong, right? You could have had a measuring tool that was incorrectly calibrated and you had no idea. You could have somebody on your team who had a bias. You could have a data, if you're doing data about people, you could have a bad sample group. You just don't know. So the way to overcome that is to make sure that lots of people get the same results. Okay, because if I test my thing and I come up with this and it supports my hypothesis, I say, great, my hypothesis is supported. That's not enough. More people have to do it. And for really good science, it's got to be tons of people getting the same thing. We don't want just 1 or 2 or 3 trials of this experiment. Any closing questions about the scientific method?